So, how was the activity? Hopefully, it helped reinforce the math concepts you learned earlier in today's program. Now, let's review. In the beginning of the program, we talked about the importance of scaling, especially when it comes to maps and models. You learned that fractions, decimals, ratios, and proportions are all important math concepts when dealing with scales. Sten introduced you to the astronomical unit, the unit used to scale the solar system. Later in the program, I have an interesting challenge for you. But before we get to that, Sten has a few more questions for you. Let's head back to Sten now and learn more about scaling the solar system.
Hey, it's great to have you back. In the last segment, we introduced the scale of the solar system and the astronomical unit. Believe it or not, astronomers once knew only what the distances were in astronomical units, not in actual miles. Recall the following chart that shows the distances of the planets to the Sun. Between 1609 and 1619, the astronomer Johannes Kepler used precise measurements of the planets in the sky to determine their orbits. But his geometric model was based on the scale of the Earth's orbit, not on its actual diameter in kilometers or miles. He determined the ratio of the distance of each planet to the Sun relative to Earth's distance to the Sun. His baseline unit, the distance from Earth to the Sun, was designated as exactly 1 AU, or 1 astronomical unit. The problem is that Kepler could not accurately determine the distance between the Earth and the Sun. The best estimates at that time ranged from 50 million miles to over 200 million miles. But by the 1890s, astronomers began to know that number very precisely. How did scientists without modern space technology and rockets do this? You can't just send a spacecraft to the Sun and back to determine the distance. Human life, including Norbert and Zot, couldn't survive the intense heat produced by the Sun. So the question for this segment of the program is, how do we determine that the Earth is 93 million miles or 149 million kilometers from the Sun? This would be a good time to pause the program and discuss the question with your teacher and your peers. So, did you come up with any good ideas? If you didn't, don't worry about it. After all, it took astronomers about 2,000 years to figure out how to do it. The answer is that astronomers used a geometric technique called parallax to determine the distance between the Earth and the Sun. Parallax is the apparent change in position of an object when you look at it from two different stations or points of view. It sounds mysterious, but you use this technique all the time. For example, let me show you how parallax works by using my thumb and that rocket in the background. First, hold your thumb out at arm's length. Now look at your thumb with your left eye open and your right eye closed. What do you notice about the position of your thumb? There seems to be an apparent change in position of your thumb from 2 points of view, your left eye and your right eye. Your brain uses this information to figure out how far away things are from you. Actual parallax calculations can be quite complicated, but here's an example of how we can determine the distance to that rocket using many of the same geometric principles. Suppose we wanted to approximate the distance between where I'm standing right here and that rocket over there. And suppose also that there was a body of water in between that we couldn't get across. Would you believe that we could do that by just using a pencil, a piece of paper, a ruler, a piece of rope, and a protractor? The first thing we do is to lay our rope in a straight line. The rope will serve as our baseline and is 10 meters in length. Standing on the left end of the rope, which we will call position A, hold the protractor so that it is parallel to the baseline. Place the pencil on the inside of the protractor and move it along the curve until it lines up with the object. Being careful not to move your pencil, have a partner read and record the angle measurement. We then need to repeat the same procedure on the other side of the rope. We will call this position B. We now have two angle measurements and our baseline measurement, which is 10 meters, the length of our rope. On a sheet of paper along the bottom, we draw a line 10 centimeters long to represent our baseline. For this exercise, let the scale be 1 meter equals 1 centimeter. Mark one end of the drawn line as point A and the other end as point B. Using our protractor at point A, we measure an angle that is the same number of degrees as the angle we measured outside for point A. Let's mark and draw the angle. At point B, we do the same thing. Now measure an angle that is the same number of degrees as the angle we measured outside for point B. As you can see, the two lines intersect. We mark the point of intersection as point C. Now we draw a line perpendicular from point C to the baseline. Using our metric ruler, we can measure the distance of this perpendicular line. Finally, using the scale 1 meter equals 1 centimeter, we can approximate the distance the actual object was from the baseline. For our case, the object is approximately 20 meters away. In this example, we used a geometric technique called triangulation, which assumes that we know the baseline length and the two base angles. When astronomers use parallax, they measure the baseline length and the vertex angle. It is hard to use the parallax method in the classroom because you can't measure the vertex angle exactly. With proper measuring technology, this is not a problem for astronomers. To refine the actual Sun-Earth distance, parallax observations of the transit of Venus were made between 1761 and 1882. The transit of Venus occurs whenever the planet Venus passes in front of the Sun as viewed from the Earth. By observing the apparent shift in position of Venus against the background of the solar disk as seen from two different places on Earth, astronomers were able to use this parallax shift to determine the distance from the Earth to the Sun. The last Venus transit occurred in 1882, and we are fortunate to have another transit of Venus happening on Tuesday, June 8th, 2004. This is an historic event because no one alive today was around when the last one occurred. To learn more about the transit of Venus, let's visit Dr. Janet Luhman at the University of California's Space Science Lab in Berkeley, California.